So today's session we're going to cover actually calculations and also enterprise, a little bit of calculations and enterprise, two topics. But calculations. So when we build, there's design build, activity, there's engineering behind that, so there's bills of materials. Some of the core things that you need to understand in order to build effectively includes knowing, okay, you're building something, knowing what are you doing in terms of strength, basic physics, gravity and strength and compression and other forces that exist on a building. So let's say we're talking about buildings or machines or whatever. There's structural strengths, there's all kinds of quantities you can assess, whether it's thermal performance of a house, how hot steel will get in the sun, whatever. Structural, mechanical, electrical, hydraulic, all kinds of calculations. I'll start with just basics of how you can, like, since we're in a builder crash course, what are some of the basic things there that you need to know of in order to be able to build effectively? So first thing I'm going to talk about is the strength of something. Typically it's called compressive strength. When you've got weight upon a foundation, you've got compression, you've got load-bearing capacity, or you've got things like studs supporting the weight of a second floor or a roof, or cantilevers or overhangs that hang off, and you've got you've got forces there. The ability of the materials to withhold forces are determined by the material that you're using. So you need to know three main classes of quantities for wood, steel, plastics. Those are the three things we work with the most. Then there's ceramics, dirt, and other things. I won't get too much into that. But for wood, you're talking about something. So calculations, I'm going to take notes here as we go. Okay, wood, steel, and plastic. Those are very common things. Plastic is, it's a huge part of the economy. Wood is a huge part of the economy, responsible for a lot of the housing. Wood and steel is basically construction. Wood, steel, and concrete. So actually we should add, we can actually get away from rocks, which are concrete, which are like on a scale of several thousand pounds per square inch force that you can load onto a piece of concrete that holds them per square inch. So think about that. Per square inch, 3,000. If you get a piece of wood, compressive strengths can be, let's look at the big figures. For steel, it's in the tens of thousands to 100,000 psi. Okay, steel, square inch. How much can you hang off a 1 square inch cable? That's determined by the tensile strength. It's determined by its essential property called pounds per square inch tensile strength. And in steel, because it's anisotropic, means it's got properties the same in one direction as another, compression and tension are typically the same. The hardest steels are up to about 140,000 psi. So if you got that super tensile cable, that's 140,000 pounds per square inch. It's huge. So if I get that rope, how much can I hang off of that before it breaks?
10,000 pounds?
100, anything, but assuming you can hold it. How much can you hold? That's the tensile strength of that. What's the tensile strength of the strongest steel?
14,000.
I said 140,000.
Oh, 140.
Yeah, mild steels are actually at around 50,000. But the strongest ones are 140,000. So how much can you hang off a little rope? You got a big wrecking ball. I think it can weigh
140,000.
Yeah, that's like 70 tons. Okay, so think about it. That's 70 tons off that one rope. Okay, next. If you take that rope, make it a little square. You got a super heavy weight on that 1 square inch. Like before, and that thing won't compress. You put that 72-ton ball, what's going to happen to that square inch? Will it compress or will it withstand it?
Should withstand.
Should withstand it. Sure. So in compression or tension, it's similar. So you have a little thing holding that big ball. Now, what if that rod was like super long, like 10 feet? Like, can you put 72 tons on it? Or at the limit, make it 100 feet. You got a rod that's 100 feet. That's easier to think about. You put a 72 tons on it. Is it going to hold it?
So you're adding
It's probably
the cable
going to
weight
bend.
itself.
No, it's you compress it. You stand. So we remove the cable. We switch to shaft.
Oh.
So you got a shaft that's 10 or 100 feet. Can you put a huge weight on that on that 1-inch shaft? What happens then if you put that 72 tons on it?
Will it bow?
Yeah, it will bow. It will crumple right under it because now you're getting into other things like bending. So as soon as you get bending, that's a different kind of a force. So you can't do it. Like that 100-foot rod, it will start sagging by itself, just by its own weight. So think about that. Like, yeah, it's 140,000 pounds per square inch. That doesn't apply to flexion. You know, you only have so much flexional strength. The kind of things we were concerned with in flexion, like if cantilevers where you suspend something off a point, like for example, the trusses we did, they stick out 6 feet from the other walls, right? So, yeah, and they support the weight of the other trusses. You're interested in forces like cantilevers and psi. So, steel, 50 to 150,000 psi. Okay, great. That gets you like a car that, you know, cars and tractors, like a skid steer. It weighs like 8,000 pounds. Yeah, you got to do steel. Can you make it out of wood? Well, wood goes from about 300 to 1,000 or even 2,000. So when you get to wood, you're now getting into the 1,000 scale. And when you talk about lumber that has knots, they derated down to about 300 level. So steel, tens of thousands. Wood, 1,000. What about rocks and plastic? Rocks are like, think of concrete. There's definitely 3,000 or 4,000 or 5,000 psi. Now that's psi, concrete. And that's comparable to rock hard. It turns from lime into, the cement turns from lime to limestone. So if you talk about rocks, concrete, you're talking several thousand psi, like a few thousand. Now that's stronger than wood, isn't it? Right? Because wood is under 1,000 for practical, unless it's engineered wood where it's above 1,000. Okay, so that's a main quantity you need to consider. What about plastics? How strong are they? Typically they're around 5,000, so they're actually stronger than concrete. Like the slab we poured is 3,000 psi. A piece of plastic is gonna have, thank you, typically more compressive strength than that. Whoa! But it also you can scratch, and you can like with a knife you can scratch probably more easily than concrete, or if it's hot it will get soft. So concrete is better for a floor. But the quantities we're talking about, 1,000 for wood, 5,000 plastics. Rocks are similar range, and then steel blows it out of the water much stronger. So why is that relevant? Well, let's talk about wood, because I mentioned that steel is pretty much isotropic, meaning it's got the same properties in one direction as another. Wood is not like that. Wood is, because steel is like a bunch of blobs of atoms that are pretty much same in each direction. If it's not a crystalline type of a metal, so it's got same properties. Wood does not have the same properties. It definitely, wood cells are elongated, they grow up and they kind of layer up. So along the grain, it's much stronger than across the grain. So that's one of the things about wood, where you have about 2 or 3 times more strength along the grain than across it. So if you have, for example, you're talking about, say, and also how the wood is arranged determines how, you know, what kind of strengths. Like think about the joists. We put them on edge, right? That's because they have more meat. But if you lay them flat, you'd think, well, why not? Why can't I lay them flat? Well, in that direction, there's less. It's much more bendable in that direction. So obviously the I'm saying a very obvious thing, like the way you arrange wood, it can flex. Now, so if you laid your joists flat, I mean, you'd totally wobble up and down and you'd break them. Why is that? That's the physics of how the thing is, or the geometry of the forces here. But the practical outcome of that is if you have long members and you're trying to push or pull them across, they're very much flexible, but not in the vertical direction. No, they do not bend. So, for example, when I was moving the 20-foot platform, I did not want to poke that with the forks. I laid a piece of wood on the 20-foot. Actually, it was the floor modules. I wanted to push the floor module across the floor to move it to the back of the workshop. I actually put a piece of lumber in front of it horizontally, so I could push against it as opposed to push against a piece of wood this way, which can bend, like it can fishtail this way. So I actually put it like that, and I could push it much more easily. So that's, practical applications of how you do things. When you have a frame that's like a big frame of 12 by 20 even, it still can wobble, just like you see with the now the taper units. They completely wobble in one direction. In the short direction. In the long direction, they're a little stiffer. Okay. So when we look at the strengths of materials, you have to kind of look at orders of magnitude. So, for example, if so we talked about, so let's talk about studs. How much does a stud hold, right? So now we've got the orders of magnitude. We've got, say, 300 for practical purposes for wood, assuming there's knots and things. Let's do that lower level that you're safe. Steel, you got tens of thousands. Concrete, you got several thousand. So for wood, then therefore the question would be, well, how much can a 4x4 hold vertically then?
Well,
Assume it's 4x4 inches, like for 16 square inches. So what do you got there?
4x4, you said a 4x4 for 16?
No, say you got that post right there. How much can it hold? Say it's a 4x4. Got that right there. What do you got?
12,000
How do you get that?
times 4.
So what are you doing?
3,000 times 4.
Where are you getting 3,000?
I think it said 2,000 PSI. PSI.
300.
Well, 300 to 100.
300.
Oh.
300 to 1,000
Or
for
in-
plain wood.
4 inches square?
4x4. 16 square inches.
Oh. Just 300?
So 16 times 300 is about 5,000. So you can say that, oh, that could ideally hold 5,000 pounds. And you might, now 300 is actually, and that's actually what,
Oh,
yeah.
16,
Yeah, yeah, that's right. When you do that, you can, I mean, orders of magnitude, the order of magnitude there is thousands, right? So even if we were off by a factor of 10, you got 5,000. If you're off by a factor of 10, it's 500. The 300 value is actually very conservative. That's what engineering codes, like if you chat GPT or you do the codes, they do it off of that conservative value because while wood may be 1,000 PSI for like high quality, number one grade lumber, no knots, yeah, you can do that. Regular wood, they actually derate it to 300,
I see.
right? So you look at that,
You don't-
how
you
many
don't
knots you got
calculate
in
it
there?
to the least? You don't calculate it to the least value?
We are. So with 300, we did it to the least. And that's what they would say. That thing can hold 5,000 pounds. So,
What?
yeah. Start looking into that. But
5 tons. That's like
that's a lot. Now, you can only do so high. Like if you made this now 20 feet, that thing is going to start buckling. So now you got to look into the condition where now it's so long that it'll actually bend and collapse. But it's not because like a little slice of that wood cannot hold. It won't actually like crush. It will bend and break. It won't crush. So if you talk about crushing force of that, assuming this was, say that was fixed to the brick wall, it cannot move.
oh yeah.
Absolutely
Okay.
5,000.
So yeah, like especially so if you put them side by side, right, where they would keep each other
Yeah.
right?
Um,
Protecting.
we're talking about just general figures here, but that's the kind of orders you're talking about, thousands of pounds. That if you got multiple of these across a building, and that's what they can do.
Okay.
So that's like basics.
I don't know. I'm having a hard time, like, because I guess it is the bendability factor.
Yeah, and we're getting into the first principle, like first order of strengths. Now,
Okay.
if you, for example, if that's an issue, then what could you do there with the same amount of lumber? You can actually make it, instead of using, say we got that let's say we're working with a 6x6, and it's a solid structure of wood. If you actually took individual, for example, like take the same amount of wood but expand it into, like, say you get a 2x10, a box of 2x10, 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 2x10. If that had the same amount of meat as a 6x6, which it's probably close to that, then the bending issues are much less. So say the 6x6 might start buckling as in bending. If you got a wider column, now you're supporting the forces that you do not get that kind of buckling. Do you see what I'm trying to say here?
Yeah, like, well, I'm trying to imagine, like, I'm trying to isolate the factors, like you say. So if I imagine 4x4 with, like, steel brackets off of the side that don't allow it to bend, that's not adding to the strength, right? It just holds it upright.
Yep.
And then I'm imagining a 5-ton anvil, like, placed on the top of it. You know what I mean? So I see what you're saying. It just
Yeah, you can.
that's and you're saying that's the low end that we did.
It's pretty much the low end. If you can prevent that from bending, then yes, that's the kind of thing. So, for example, say you've got, you're looking at, you're building a bridge, and you've got these short little members of 4x4. Yeah, they can absolutely withhold that amount of compression. Now, what if it was going to actually torque?
Sure.
Yeah, you have to consider other things, but here we're talking about just getting into basics of the kind of forces that you can withstand.
Isolate those factors in my mind so that I can
and
conflate them.
Yeah. So what if that post was made, so here we're just looking at the biggest picture considerations. What if that post was made of steel? How much could it support?
As an I-beam, or just in its same shape?
Well, the I-beam, they do the I-beam precisely for that reason, where they cover more footprint space so it doesn't bend one way or the other, and therefore compared to a straight rod, they spread that meat out into an eye which has more area that resists buckling, right? But let's not even get into that. You're talking about an I-beam. Let's just say a 4x4 of steel. How much can that hold? Say that post was made of steel.
140,000 times 16?
Times 16.
Yeah.
140,000 times 16. That's millions of pounds. And that's true. If it doesn't buckle, it's holding that much. Now you might see a bridge that's made of a triangulation of that, because that's what prevents it from buckling in the other directions or torquing or doing other things. Well, I'm trying to get you here to understand the very basic things, like what we're working with here. Now, what if that thing was made of compressed block? So let's just play with these numbers here. And then what would the practical consideration? Those walls are compressed next to it are 6-inch. They're compressed block. How much can they hold on the top? Okay, so let's take that brick wall right there. We got a 1 by, the end wall there. It's 6 by 12 inches. How much can that thing hold? So now we didn't get into dirt, but dirt is actually from 300 to 1,000 psi about for the bricks we measured that we pressed here. We measured that on a press, a hydraulic press that we could read the pressure off of that.
How do you measure the pressure?
How do you measure a pressure? So we pressed it with a cylinder of a known surface area. We know the pressure, a hydraulic pressure behind that cylinder, so we know how many pounds of force are being spread across that press plate, which was 6 by 12. So from that, you derive the pounds that you're pressing on that in pounds per square inch. So if that makes sense, that's the basic process. You measure, I was looking at the hydraulic gauge, it tells me the pressure, because basically as soon as you hit the block, the gauge goes way up and it goes to a number, say it was like 2,000 pounds per square inch for the hydraulic pressure, and it still held it, right? So you'd convert that 2,000, after 2,000 it went to 2,500, 3,000, crushed, you know. Okay, before the 3,000 I was at, say, 2,500 or 2,000. I convert that number into actual pounds per square inch on the pressing on a block based on I had a 5-inch hydraulic cylinder, I had a 12 by 6, 72 square inch press plate. So that, all that pressure, 3,000 times the area of 5 diameter, spread across that, it turned out to be like between 300 and 1,000 or so psi. That's how we measured it. So back to the practical question, if those bricks are 300 psi, so now dirt, we're talking dirt. It's less than concrete, it's absolutely less than concrete, but concrete is only 3 times as much in terms of compression strength. Now there's other things like brittleness, like how it clumps together. But if you got 300 psi, how much can that wall hold?
Well, I was actually going to ask, also there's another factor that my understanding with a lot of natural materials, where you are making layers, that if you add any horizontal layer in between, that it exponentially increases that compression strength as well. Like even like sand, you know, you've heard the whole thing with the sand and just one paper towel in between, all of a sudden it's like so much stronger with just those little layers in there.
You might be considering a case where, like for example, I'll tell you with the brick, if you just have one brick and put all that strength on it, because you might be pressing like right on the edge corner, all of that will crumple, and then it'll do like a cascading effect. But if you have a whole surface of them, that's probably what you're talking about. It exponentially increases, but up to its theoretical value of 300 to 1,000 psi.
Right.
Okay, but let's take the ideal brick that where the corners haven't gotten chipped and it's actually holding together, which it's not, because on the edge of the brick, the corners are gonna start giving away because they don't have.
The brick in the middle. The brick in the middle of the pile is what you're talking
Theoretically, theoretically that brick is in the middle of other bricks. How much is that one brick responsible for holding? Well, 300 times 72. What's that? It's like 2,000. It's like 2,000 pounds for that. So in other words, that wall section, if it's 4 feet, say you got a wall that's 1 foot thick, because that's how we built them, and you got 4 feet, that's 8 times that. That wall section itself can hold 16,000 pounds, assuming that the actual load is way below that, so you're not getting into these other crumpling or other edge effects, so-called. You know, so get a load of that. What can you put on a brick house like that if you actually made the walls proper? Or you can drive on top of that. There's no problem. It can hold a lot of weight. Compressive strength, it's typically comparable to wood. You got that brick wall, it's like having a thick, like a 12 by 48 solid stud. That's huge. So if you think about the strength of a brick wall, and this is compressive block, oh, it's huge. And then another question might be, okay, so say you're stacking these bricks. People ask me a lot of times, how tall a building can you make with that? Well, the limit of that would be because the bricks are heavy, they're very heavy, right? So the brick on the very bottom bears all the bricks on the top. How tall a wall can you build with that ideal one brick? How high can it go before you collapse it? Yeah. Collapse the brick on the bottom, which feels the most pressure. So that's a little simple calculation question.
Yeah, you have to calculate the weight on top of
those. So let's just say each block, because we measured it, it's about 20 pounds, right? So 20 pounds and 6 inches tall. So what's the overall bearing strength of that? We just said 6. What do we say? We said about 300 times 72.
And then it would be
that's like 2,000.
But then minus however many bricks are on top of it.
Yeah, how much does each brick weigh? We said 20 pounds.
Yeah.
So how many bricks are going to be 1,000 pounds?
Oh.
No, we said 2,000. So we got 20 pounds per brick, and we got 2,000 pounds that a brick could bear.
100?
So
Wait, 2,000. I don't like that. No, I don't like that. 70. We're one order. This is orders of magnitude. 300
times
times
72.
72. Oh, that's not 2,000. That's 21,000.
Yeah, I was going to say. Okay,
Right.
I wasn't sure which number you did.
20,000. Okay.
Okay. So the answer is negligible effect of the other bricks upon it, right?
Exactly. So if you calculate,
Right, structure that you're building.
yes, the absolute limit, if we just said 20,000 pounds about, 1,000 bricks times 20. 1,000 bricks. That's 500 feet high.
We're not building the Tower of Babel, so.
Yeah, but that's the theoretical limit, i.e. to build structures that are multi-story is not a problem. You see a lot of these like 50, 100-foot tall structures, like I guess like in Nepal too. I think they had that there too. I remember some of those where it was compressed block in a dry, I don't know, some dry areas. I've seen like the oldest CB buildings are like hundreds of feet tall actually, and some
Yeah,
of them
they're-
are still standing. So
They're the original Towers of Babel.
there you
They're
go.
Awesome. They're still there.
Okay. So orders of magnitude, we just missed that 10 there, but I mean, yeah, this is for real, the theoretical limit. And then when you've got practical considerations, you might derate that by a factor of 10 for safety. So say like all those edge effects, so, well, it's not going to be 2,000 bricks, it's going to be 200 bricks or 100 feet up, but still, that's 10 stories safe, right? So cool. There's your answer, like you're starting to engineer the building, and you say, well, how thick a wall can I do for a 10-foot building? Yeah, you can do a brick wall that's one foot thick, and it's absolutely will hold it. But you can't do a brick wall that maybe is like a couple of inches, like of dirt. I mean, that's the edge effects become much stronger, and like the numbers start decreasing. That no, you can't do like a 100-foot building with just this much. Goes out of steel, yeah, you could, because steel has got compared to that, you got 50 to 100 times. So for a steel building, it's like, oh yeah, you can go really, really high. And then you can calculate what's the tallest skyscraper before it actually starts collapsing on its own steel, and that's like, you know, close to a mile or whatever it is. I didn't do the specific numbers there, but we can really quick. How much would so the theoretical limit would be the point at which the steel structure actually starts to compress from its strength. So we said that a 1-inch, take a 1-inch rod. Say the skyscraper is made of like a 1-inch wall, and it just go high as possible. It's got a solid footprint, say like 100 by 100 feet, or like even an acre, like 200 by 200 feet. It's made of 1-inch thick steel. At which point does that steel start to collapse on itself based on how much steel weighs? Well, you got that steel at the bottom can do, say, 100,000 pounds. How far does it get you? It gets down to the density of steel, like it's a kilogram per like 10 cubic centimeters. It's like it's comparable to an inch. Like a kilogram would be like a couple of inches, and that weighs 1 kilogram. You know, say hand waving. A kilogram is like this little mass of steel, let's say, or pound. This little ball of steel. But if you got 100,000 times that, so you multiply that, say that 2 inches times 100,000. So what's that? 2 inches times 100,000 is 200,000 inches before that steel starts to collapse on itself. What's 200,000 inches? Well, that's about 20,000 feet, or 20,000 feet, several miles. So yeah, you can in theory do that. That would be like the absolute limit. I mean, that skyscrapers get close to like what's the tallest skyscrapers? Like a kilometer or so, whatever. Yeah, they get pretty high. So yeah, you can do that with steel. You can't do it with dirt. You can't do it with just concrete. Can't do it with rock. Can't do it with wood. But steel definitely gets you there. Okay, so just rough orders. Like you can actually start calculating these things. Like, wait, is that skyscraper gonna work? Like you look at it, it's like, oh yeah, that'll work because it's within the strength of steel. But if you try to build a wood house of that, you have to stop right there. So orders of magnitude are important. Practical examples. We talked about the example of the fasteners with being twice. For any fastening that happening, you want to keep it twice the thickness from the edge, and that's important. Like when you're doing, if you're nailing onto for example, a 2x4. Say you've got another 2x4 on it. Yeah, you're reduced to. I will ask this question this way: if you're nailing a 2x4 to a 2x4, and you've got a nail going into it, what's going to give first? The nail or the wood? Well,
Yeah,
let's
what's pushing on it?
let's do that as a simple example. We've got a 2x4, and we're going to ask, what's going to fail first? Is it going to be that? I mean, this is like things you can evaluate in some practical purposes. So say you're pulling on, you've got one nail on the board, and you're pulling that board stuck to something else. Say you attached, say we're pulling something with a tractor, and we nailed a long strap to the tractor that's really strong, and we're trying to pull, like say we're trying to pull that one wall. Say we attach a nail that board, we clamp down that belt with a bunch of nails. Let's do this example. How many nails would we need to go into that wood before that something would break? The first question we would ask is, what's going to break first? Is it going to be the wood or the nails? Well, if you have enough nails, the wood's going to break first. If you don't, so let's take the case where we have one nail as a practical example. You got a 2x12 attached to your big belt. It's stuck into another 2x12. Let's assume that the nail holds. What's the ultimate strength that nail could hold, assuming it didn't bend? Because I mean, it's going to bend out.
The wood's going to be weaker than the nail, won't it?
It's weaker, but there's way more of it. So let's start. So we're looking at a practical example of thinking through a problem. Like, okay, we're trying to pull this thing. We're using nails. Ideally, you'd like use a chain and be done with it, right? Like, you have no question that chain would hold. But say you can only hold it with nails. You start thinking about it. Oh, can I even do that, or is that just a dumb idea, right? So let's take a look at what one nail can do. Let's assume that nail is so long and so strong that the wood's not going to pull out, because the wood is like hedge posts, which are like 1,000. Hedge is probably like over 1,000 psi. It's almost like a rock. Osage orange, for example. You say you stuck this nail hard into this huge block of wood because you had that, and we say, okay, we're going to pull this with this nail. When's this nail going to break? That's an application of the tensile strength. So what's a typical nail? Like, what's the diameter of a nail? It's 1/8 inch. So now you're talking about 1/8 inch. Say that thing is stuck like crazy to that. The wood it's stuck in the wood good. Wood's not going to give. So anytime you do an thought experiment, you have to make assumptions like, okay, am I right about that? Will that nail break first or not? If it's hedged, then you might be right and probably say will be. If not, then the calculation is bad from assumptions because you didn't assume right, and actually the wood gave first or whatever. So you that totally makes no sense, and that's actually a warning for whenever you see like people are coming up with these, some X and Y is going to happen here and there, or like, global warming is going to come up in 20 years. We're going to burn up to Tennessee, whatever, or this building will collapse because it's too old. And there's a report that comes out and they tell you to tear it down. Well, all that depends on assumptions that you're making. You cannot ever, by principles of general semantics, you can never know reality. I talked about general semantics and mental models. You can never know the exact reality. Like scientists and people will take measurements. Maybe, okay, you measured it accurately, and yes, you know that the building is going to fall down. But any kind of assumption or problem or conclusion is based on assumptions you're making. So if your assumptions are not good, your result is going to be not good, and that's like a very basic principle. So when you actually listen to scientists or so-called experts tell you something, if you can actually go underneath to the first principle calculations, you can say, oh, okay, your first question is, like when you see something, it's like, okay, cool, you're a scientist, you don't go, your first response is not freaking out. Because people say all kinds of crazy stuff. So say there's some scary, horror monger out there. First thing is, okay, what assumptions did they make? What did they put into that conclusion? And so forth. So that's like, I'm making that point about do not trust any experts until you actually look at what their assumptions are, if you're at the point of verifying whether the experts said whatever they said is true or false. Now, you can be a complete subservient individual and just believe everything the experts say. And most people do that. I mean, most people say, okay, these, you hear that all over the news, it's such and such. And when you do that, you are completely deprived of options, because you listen to, they say what's possible. And that's what we do here is actually the complete opposite. We just say, oh, like back again to the truss example, the engineer would have told me you do that on 1 foot center, and it's like, no, I don't. I do this, and I can do 2 feet because I did it. I put other assumptions, I put other structure and other design into it, and therefore my answer is different. So the big point is you got to be able to. What I'm trying to talk about here is some basic concepts of first principle calculations. How do you actually start assessing all those values to know what's right or wrong? You got to start with the 100,000 psi for steel, 1,000 for wood or less, concrete and plastic about 5,000. Okay, bam, there. You can get a lot out of that. Okay, so let's take a look at an example where we nailed that piece of hedge together and we're pulling it with a tractor. How much can we pull on that? So this is like a practical example. How much can we, or even to simplify, assuming that nail is going to like literally break in half because you're pulling on it so hard, how much force can we put on that 1/8 inch cross section nail? Let's assume it's a square, for simplicity, it's like 1/8 inch square. So what do you got there? What's the quick answer? Quick answer is, like, if you do that in your head, is how much?
2,500.
Around there. Like, so if you take the max, say it's 100K for steel, or say it's like a mild steel. Well, probably the nails are going to be like probably around 100,000 psi. So how do you get 2.5 thousand?
It's 140,000.
Yeah, I mean,
1/8.
that's like max. That's like spring steel, which is super hard. They're not typically making nails out of that. Probably nails are 70 to 100,000 psi. Let's say. So you're dividing that by the 1/8. So you're taking 1/8 of what?
140,000.
So it'd be like 20,000.
Yeah.
1/8 times 1/8. The area. Area is not 1/8. It's 1/8 times 1/8. That's 1/64.
Oh. So
So you're talking about like about 100th of that, of the value of steel. So if you had 100,000, 100th about is about 1,000. That's when that nail is going to break. So you can start thinking along things like that for how strong things are and etc. So for example, what about if you pull like a piece of stick, like that little stick of that, if it's got only 300 psi and it's 164, like about 100th of that, what's 100th of 300? You'll pull that little stick with like 3 pounds, you'll probably break a little twig, you can break it with like 3 pounds. Yeah, that makes sense. And you can think about various things like, you can, once you start looking at the actual physical properties of the materials underneath, you can start getting ideas of, okay, what will it do? So for example, if we're putting in, like each truss, we have each nail do through the OSB. We've got like a 20-foot truss. We put 40 nails into that OSB, into the 2x. How much are we holding there? Well, let's assume the limiting, it's close to the edge. We didn't even make that 2x factor from the say 1/2 inch OSB, that would be like 1 inch. No, if you're hitting a stud, you're only like 3/4 inch. So let's assume that the OSB will give first. So what's your limit there? Like, it's the limit of the nail and OSB. Let's say the max limit is, I kind of feel it I've seen it from experience that the OSB will like typically give first. I've seen. But let's say the OSB gives first. What's your, how much are you holding there? Like, what are you holding there? How much is each nail holding? Well, we know that nails are good for about 100 pounds. After derating we just talked about like 1,000 pounds, right? But they rate nails as about 100 pounds. So that's actually, now you can start understanding that. You go look at a table and it'll tell you a nail, a standard nail, which is about like maybe 1/8 or something, round thing. They'll tell you it's good for like holding 100 pounds of shear or whatever, or pull out. That makes sense. It's 10x factor. So you're already looking at, okay, I know from first principles that nail maxes out at 1,000 if it was 100,000 psi or so. Rough orders of magnitude. So 100, yes, that makes sense. But if you got like 40 of those nails on your OSB truss, that's like 4,000 pounds of holding force. Hey, that's pretty good. You know that OSB is not coming out. What if you went like every 12 inches? Okay, 2,000 pounds. What about every 2 feet? That's 1,000 pounds. Oh, that's getting down there. It's but yeah, you can start looking at your nail schedules, and you can actually calculate like how many nails you need and so forth. So it's useful to have those first principle notions behind you. But then let's talk about when you got the walls plumb. Like, what's the limit before things start to? If you have a vertical stud like that, what's the tolerance for it for being vertical? Well, the way you analyze it is if it's off a little bit, you'll see that, oh, well, if it's off enough, it's no longer, the force is not already pressing down, it's going to be pressing off that, is going to want to do that. Well, how much is that? Say you got a 4x4 for practical purposes. How much can you twist it to, say it's 8 feet, how much can you twist it to the side before you got, like, it's not pressing into the ground, it wants to collapse? And the way to think about that is, in a force diagram, this is a practical thing, because you're going to ask, okay, so this wall didn't exactly end up being plumb. Say it's like way off, like an inch or two, and then you ask yourself, is that acceptable? What else is what's going on here? So you have to analyze the whole situation, see, it's like, is that just that one little wall section that's 2 feet out? Or is the whole wall out? So let's take a look at that as a practical example of force. So you got your, yeah, go ahead.
You're talking about what the nails are worth and stuff because it tells you?
Yeah.
But what about how you were saying, like, not trusting them? Have you ever tried to make sure that they're being honest on what they can handle?
We just calculated and we verified their figure because we just said that a piece of steel that big holds 1,000 pounds. They're telling me a nail is going to hold 100 pounds. You guys are fine. I'll believe you. It's 10x.
Okay.
It's a whole order of magnitude.
Checking, because especially nowadays, maybe they're making it with less quality.
They're cutting the gold with the lead on the nails. Yeah, I mean, sure. And then you kind of look at it. Okay, what's happening there? And you can assess it like, okay, so they say they watered down this tool and they made it thinner or whatever. So you look at it and you say, okay, well, is that steel or is that plastic? Well, if it's steel, it's got that much strength. So you can kind of calculate for yourself. If it's whatever that item is that going to break easily or not? You can look at those, 100. For mild steel, it's typically, when we talk about tractors, it's typically around 50,000 psi. So that's like the weak steel that's easy to bend, easy to weld. It's malleable, quite soft. It's a soft kind of steel, 50,000 psi. You think about that, and you say, oh, can I, in a frame? Okay, practical tractor design question. Frame. You got this beam here. You got steel. Can this thing, it's my frame, and you got wheels. This is structural calculations 101. You got wheels. I'm just going to draw a quick tractor because this is what we're going to do in the coming months. We're going to calculate, well, what's the frame? Well, we already kind of know that the thick tubing we use already can hold it. But if you had a beam of steel, like say you're using a 2x2 inch solid rod, you know, how much weight can you put on that before it starts to collapse in the middle?
And this is steel.
Yeah.
2x2.
Well, or let's even, well, how do we want to do this? So now you're getting into bending moment calculations, and that's different. That's the cantilever stuff. Like when you have, say, a tractor with wheels, like how much can you press down in the middle?
I was going to say, wouldn't it matter where the weight is,
It
too?
is.
If
It
it's
does.
spread equally, it's not going to bend as easily if it's all in one spot in the middle.
Yeah, yeah. But say the frame is like this, and it's also got vertical members. That gets into. I won't get into that. That's you simply look at like the way you calculate it. You can either do in FreeCAD. We're going to teach you how to go into the finite element analysis module of FreeCAD, where you draw it a shape, and then say, okay, slice it up into little parts, and then put a weight on it, and tell me how much force I can put in it before, like, the force, like, say this was a cantilever.
Causes it to change.
Yeah, like, you'd get this graphical visual representation. So you do the force, like, literally. You got this down force here on this thing. It's got this cantilever on these wheels, right? You tell FreeCAD, okay, you got this force here. It'll draw you a diagram which shows like from green to red where the scale of the force is. So yeah, you've probably kind of seen some of these diagrams.
So that's
but you can actually have FreeCAD calculate, because to do those bending things, you have to calculate, because it totally depends on the length and so forth. Is it a tube? Is it a solid shaft? So that's complex. Like
Right.
you can't get that like just in a second. But you can go look up a table and say, what's the bend
Ratio.
deflection? So you go up to Google now and you say, what is the deflection of a 2-inch rod from a support point 4 feet? So it, so you got a cantilever of 4 feet. You're pressing down on an end of the rod like that. That's 4 feet. What is the bending moment? Not the bending moment. It will be the deflections. These are deflection calculations, which are very common in all kinds of studies.
But that would be like a skid steer right there. Why it
Yeah.
doesn't flip on you because not to
Yeah,
put
that's
too much on
that would be just gravity. That in that case, what you're discussing is say we got a loader on the front and a gravity in the middle, acting on the body of the tractor. Then you're just calculating what's that force compared to whatever is happening on the other side. But let's finish the bending thing. You can calculate and you can use FreeCAD with finite element analysis, but the practical consideration here is, no, you're not going to do that, and you got different materials, so you just ask Google, what's the bending, the deflection? It's called deflection. So deflection calculators. Google up a deflection calculator online, and you say, what is the deflection of a 2-inch steel shaft supported 4 feet away from the deflection point? And it'll tell you. And it might say something. So then how do you interpret it? So it might say something like if you put 1,000 pounds on it, the answer, or even 10,000 pounds, the answer might be like 0.5 millimeter. What's that mean?
That's
Well,
how
that-
it starts to bend at that weight? Or
Yeah, but that means hardly nothing. Like you won't even see it. So you take that result and say, okay, that's cool. Because your problem statement was well defined. Say I want to design this house so I can walk up there and have thousands of pounds, a bunch of people, we got a veranda or whatever. Do that. I'm just asking it. Okay, I want to put 10,000 pounds on there. What will happen to that steel or that wood or whatever? And that's deflection calculators online. So you can readily, like, say you want to stick out a piece of wood, a 2x4, or steel, and you want to see how much it bends. If the answer was like, 3 inches, oh, that's like, that thing is just going down. You got to start watching it.
So
But if it's like a sub-millimeter or like an eighth of an inch, it's like, you can hardly see that. That'll work. No
so
problem.
like the Maysville house that we
Yeah.
went and toured, that veranda, if someone wanted to put weight equipment out there, you
Yeah.
have to know what it could handle because you start getting into 500 pounds if you're putting weight benches
Yeah.
out there and stuff.
So you've got 100 gorillas out there that weigh, or 50 gorillas, no, 10 gorillas. That's 5,000 pounds. Their weight. That's a thing you can actually read right off tables. You can say, for a deck made out of 2x12s spanning 20 feet, they will tell you what that weight ability is. Like they might tell you it's like whatever. Typically, the way it works with trusses, like in that porch setting, say you're calculating, they'll tell you how many of them do you have to have in order to support that, 5,000 pounds, like say 20 people there on that deck, and that's a reasonable figure, like 5,000 pounds on a deck, like weight of a car. I mean, that's pretty heavy.
If you wanted
But-
double, you would just add more trusses in there,
Yeah,
right?
yeah. In that case, you just double up the schedule, and that pretty much works there. But it does not work for extending this thing because you get into that bending stuff. So here, yes, you can double up to a certain point. But when you at the limit of infinity, it will break upon its own weight. So this does not. It's non-linear in terms of lengthwise. That's why the 32-foot trusses that I'm talking to you about are a great accomplishment, because the 32-foot truss, like we have a 32-foot span in the current workshop, very expensive. Those the longer you get, like it becomes exponentially hard to keep them from deflecting in the middle. And that's why in our design we have an effective span of only 20 actually, because those supports are holding it like 6 feet from each end, so that's 12 feet. You've got 32 minus 12 is an effective 20 span. So we just reduced that design into 20-foot spans, like the deck on a. So it's much easier. So
Which is
things
why
like
it
that,
works.
which is why it works. Okay, so say we're doing this for steel. You got deflection calculators online. We do that all the time here. That's why I'm bringing it up. If you have, for example, a 4x4 tubing frame on a tractor, say you want to, you got your tractor box frame. You want to, like, I want this tractor, this skid steer. Well, I mean, industry standard is 5. Like, that skid steer only carries like 3,000 pounds max. That's like, I'd like to actually design ours for 5 or 7.
Same size.
But say we want to carry like 7,000 pounds. So you got the frame like this. My question is going to be, is my 4x4 inch tubing going to be okay, or am I getting into like danger zone where that thing will collapse? So say I want to design it out of 4x4 tubing, 1/4 inch wall. So that's my tractor frame. I'm going to put a loader to the front. I want to say, okay, if I hang my loader arms. If I hang my loader arms from the front beam, which I don't, it's typically you hang it off the back, but let's say I hang it off the front. With a 4x4, say I have a single 4x4 in there, I got this weird design where I got this one post. Assuming it does not bend or wobble, would a 4x4 made of 1/4 inch steel hold 7,000 pounds? Just from first principles. So 4x4 steel, it's hollow, it's 1/4 inch, so once again, PSI, pounds per square inch. So you count up the amount of square inches you got there for how much it can hold. So how many square inches in that? Each 4-inch wall's got about an inch. It's about 4 square
I was gonna
inches.
say, but it's hollow, so.
It's hollow, so it's only like 4 square inches. If it's 1/4 times 4 inches, that's 1 square inch. You got 4 sides, so you got 4 square inches. Is 4 square inches of steel going to hold 7,000 pounds? Yeah, it
What's
is.
the
Because
PSI
we said
steel?
it's 50,000 psi for mild
50,000.
steel. Yeah, you got 200,000 pounds that you can hold. So you know that if you use 4x4 steel tubing, now assuming it doesn't bend, so of course you got to make it into a cubic frame, that it's solid, other things. But from first principles, you start with, okay, what kind of material am I going to use? Well, 4x4 tubing is more than enough right here. So great. We can go forward with 4x4 tubing, let's say. Because we know we've got way more than, like, say we want to lift 7,000 pounds, we got way more. Now, if you want to calculate exactly how this thing would react upon, the tension on the joint there with a shaft through it, there's a pin through it, like what are all the forces there, detailed like in every square inch of this frame, then you have to throw that into FreeCAD and let's say you go through finite element analysis and say, okay, what are all the loads everywhere? And you look at those loads and you look at what you got, like say you put a shaft through the right through the half-inch steel, the quarter-inch steel, and you've got 7,000 pounds. Like, well, typically people use bushings because that steel, if you're going only against like the wall, the quarter-inch wall of that steel, it'll just start egging it out over time. Now 7,000 pounds, that's the weight, but impact loads are what you're gonna have to consider. So we calculate from first principles. Okay, we can hold like 200,000 pounds, but what if you just ram that tractor at full speed into a brick wall or a tree? What's gonna happen? Well, we just calculated in theory that, okay, say that 4-inch tubing gets you like 200,000 nominal pounds of strength. How hard did you hit that tree? And if we're talking about 7,000 for a standard load, impact shocks are typically, the rough number, the hand-waving figure that engineers use is 10x. So you're designing not just for that weight of 7,000, you're designing for, like, say you get into accidents and you hit things, impacts, or you're going fast down a road and you got hit a bad bump. Those impact impulses typically add a 10x factor to what you need to solve for. So when we calculate 7,000 pounds, like say your loader, the hydraulics went out and just dropped with 7,000 pounds on it. You can easily count that the impact there was like 70,000, 10x. Because it's basically like, say you hit the ground and it kind of like gave in a little bit, but it stopped it pretty short. Impacts are typically counted as 10x. But yes, that steel, like in principle, if we use that quarter-inch 4x4 tubing, it would actually still hold it because we just said 200,000 pounds. So yeah, you might actually survive that accident without any damage to the thing you're working with. Okay, these are all kinds of things that when you get into the process of designing new things, you have to consider, and I'm just going through a few things here. I didn't get into this thing of how much off a vertical can a wall be. And let's take a look at it. You got an 8-foot wall. Say it's a 2x6 wall, so it's 5.5 inches. Because this will tell you like the basic analysis for what's acceptable. So you actually, when you're building, you don't have, like, for example, nightmares like, whoa, is that going to fall down? Because you can assess what's going to happen. So take a look at this. If your wall is 5.5 inches at the bottom, what happens? So you got the force going, you got load on the top, right? At it. Are people still looking? Yeah, there's still on there. So say you've got a load on the top, which is like, say, the entire weight of the house. It's going to be thousands of, if the roof is 50,000, 50 PSF, that's the rating we have on the roof right now for the trusses. 50 pounds over 720 square feet, the max load we need to hold is, holy cow, 50 pounds times close to 1,000. Close, it's going to be like 30,000 pounds, close to 50,000 pounds, let's say. Okay, you're spread over a lot of the walls, but you've got, say, a couple of thousand pounds each wall needs to hold. It's 5.5 inch. Our question is, are we plumb? The question comes up on the field. Is that good enough? Are we plumb? Okay, say it was like a degree, a couple of degrees here. So what's the number of degrees? Like, minimum I can do is like, not 0, but let's say, about 3 degrees. That's all I can draw here. Okay, if you look at the force diagram on that, assume the force, here's how you do a force diagram. Assume the force acts in the middle of it. Cool. So you draw, that's in theoretical force diagrams,
The middle
yeah.
of the building or the middle
Well,
of
like,
the material?
there's a load on top of this wall module. For analysis, let's take a look at, one good assumption is that the force acts in the middle of something. Because it's kind of true. Like, if it's spreading its weight over the entire thing, it's like having one force in the middle.
Okay.
It's similar to that.
All right.
But still, once again, keep in mind, this is all just assumptions. And under some other assumptions, no, maybe you can't just put that load in the middle, because that's not how it really works. But for here, let's say it's good. So say you're pressing straight down on that. And our question is, holy cow, are we going to be kosher on this angle? So I'm going to draw that line straight down. So I just drew it straight down. Okay? So what's happening here? What we're seeing here is that now all that force, because this is now like almost off the ground, it's only this part, and this is once again hand-waving arguments, but here we've got just this amount holding that weight, so you're really stressing out that corner of the wood, right? Maybe or maybe it will not hold. I mean, it's not designed for that, it's designed for the whole bottom to support it. So here, if we had the force going down like that, it's acting, you know, through the middle. Okay, cool, great. Here, what you're seeing, you've got a problem here. It's only this much of the wood is actually supporting it. All this stuff is doing nothing. It's like it didn't exist there. It's doing something because it's actually connected to the rest of the wood, so those fibers of wood are actually holding it, but you're actually literally starting to shear those fibers of wood. Okay, this is getting dangerous. But what if you're like a quarter of an inch that you hardly see? I mean, you know, say you're bent, but you know, it's like that's skewed like only that much. Well, I don't know, like if it's significantly less than the side that you're on, like if it's 5.5 inches, if it's a quarter inch, if it's at least 10 times less would be half an inch. You know, half an inch is still kind of acceptable. So in the codes, they tell you what's the acceptable tolerance for vertical over 8 feet. I think that answer is like a quarter or even a half. Let's Google that because that's a critical thing. By code, they say on a wall you can only be, to meet code, the inspector will fail you if it's not within so much of vertical. Let's Google it. I think it's, my guess it's quarter to a half. What is code approved off vertical for a wall for an 8-foot wall in inches? What's the answer? Yeah, it's a quarter inch.
And by code, you mean international
Oh.
code, IC?
Allow for, some guidelines are slightly more lenient, but 1/4 inch is a standard for good finish work, especially with drywall and tile. That's industry-specific guidance. So I'm assuming that in Walken you get into, in fact, light wood frame. This looks more like codes to me, but here it looks more like, because I was actually surprised when I was looking at the codes. They still pass you if you're like a half inch off, and I think that's about right. The residential construction performance guide suggests a tolerance limit of 1/2 in 32 inch horizontally, or 1/2 inch 8-foot vertically. Okay, so there you got the answer. It's actually half inch. Yeah. Okay. I think we got. I think in our house we're on that. But what's the danger zone here? Okay, here you're literally getting to, this wood is going to get crushed because effectively only this part on this side of that line is catching all the force. If you bend it even more, you can assure yourself that a theoretical catastrophic limit, okay, so it's bent, say it's like that. What happens when that force now starts going over? You see the detail there? That force pressing down is over that edge. That means that at that point all the force is actually collapsing that wall. It's no longer even supporting it. So, I mean, that's limit. But by code, let's just say half inch. But for your personal understanding, like say by accident you had a case which is comparable to this and you're asking, okay, that's bad. Is it catastrophic? Okay, well, is the rest of the wall good? Is that only like maybe one wall sections out of all of them where you've got certain loads and you know all the other walls can hold perfectly fine? So if you had this mess up you're evaluating, it's going to take you like say $1,000 or $10,000 to fix it. Do you say, am I going to leave it or am I going to fix it because it's catastrophic in terms of actual danger? Well, you have to assess it. You know that there's a real possibility of danger here. You know that if it's a half inch, no, that's even code. you know that if it's like a couple of inches, well, you get into like the real compression. You literally decrease that whole. It's like holding that whole wall with like a 1x, you know, that gets bad. So probably not. You might not want to do it. Okay. Or yeah, oh yeah. Actually, this morning, just to review that little thing, the scab for the scabs of when we're scabbing up OSB. We kind of calculated, we went through a discussion there that the minimum would be 2 inches on each side. That's very common here, but if you talk about ideally, okay, so that's when you use fasteners, but what would be like the theoretical limit, assuming, like say you could weld wood together, and you could weld weld the two pieces of OSB together, would that weld be sufficient? Because say you had like super crazy glue that's stronger than the wood, can you just glue that gap? If it's stronger than the wood and it binds stronger, say you got glue that's like epoxy glues, they get up there, like I think epoxies get up to the range of hard plastic, which are on the order of thousands of psi. So say you got really good super glue that's 1,000 psi and you're gluing the wood together, is that cool? Or can you do that? And how much glue would you need theoretically to do it? I mean, well, if it's a brake, you got to fix the whole brake. So but I'd say that glue can do it if you had a means to do it. I mean, these are just crazy questions. Like, you're going to run into all kinds of insane problem statements throughout the build process, and you got to have a way to evaluate how you're going to approach that problem. So say you got to fix some structure, you immediately go to the PSI strengths of the things you're working with. For example, if you said, oh, I got foam, I'll just put some foam in there and it'll close it up. Well, what's the compressive strength of foam? It's like 10 psi. Well, so if you fill that crack with foam and it's 10 psi, like I know, for example, the floor, like the foundation boards for the board foam is like 25 psi for the good stuff. The other soft stuff is like 10 psi. So say you got hard foam that's like 25 psi. Well, what's wood? Said 300. OSB is around, they calculate about 300. They do it at the lower limit of all woods, which are 300 to 1,000 or so, because OSB is just glued together. It's glued together particle board particles. But okay, so that foam, you can't do it. 25 less than 300. First principles. No, ain't gonna work.
What does OSB stand for?
Oriented strand board. Look at that.
What?
Yes, it does.
I've never heard that.
So think about this. So on oriented strand board, you can also you can calculate. Can you actually? What happens if you heat wood? It actually. Well, if you heat it, you can actually melt the lignin, the lignocellulose part, the lignin. So actually, the way the natural OSB. So this is a diversion now, getting into hippie land, into products like straw board. All you need to do for OSB, so industry does these toxics for OSB. It's it's got fumes, it's formaldehyde or whatever it is, the glues that are in there. If you've got chemical sensitivities, you can't really live with that. So what's the natural way to do it? And then you look at other options. The glue, they glue it, and the glue must be stronger than the wood itself. Otherwise, the OSB would not hold together. So okay, but let's look at naturally glued. You know that lignocellulose, wood is lignocellulose, and it's got lignins in there. They melt at high temperature, so you can actually heat treat things like sawdust or strands like chips and press them together, and that's the natural version of the oriented strand board, which is chemically bound today. That's the oil industry, right? So now you get into, well, maybe that will take reasons why it doesn't happen is, of course, industry inertia, because that's a thing. If you need heat or electricity to do that will cost you in electricity. But now, remember we said solar energy is near free now, zero marginal cost. So for this reason, I'm going to claim right here tonight that natural oriented strand board glued by its own lignins with heat and pressure is the future of OSB. and it's going to not
That's
smell.
a hot stock tip right there.
So that's $1 trillion proposition right there, because not trillion, it's a several billion. OSB, market size of OSB is probably on the order of a couple of billion. Housing is trillions. Now OSB, that's a significant part of that. I would say OSB is like maybe it's at least 1% of the cost. It's probably a few percent. So a few percent of trillions, that's like tens of billions. What's the market size of OSB? I just did a first principle calculation on that. Just big numbers, but here once again I'm saying, okay, there's orders of magnitudes. If you understand those, you can start coming up with creative problem statements that are not just BS, like somebody will come, oh, I got this idea. No, they're actually backed up from first principles, so you can actually take a stand on working on them like we're doing here, trying to save the world. So what is the market size of OSB?
Can we make the new standard size for this lignin natural wood a 3x6 instead of a 4x8?
Why would you like to do that?
So they're more manageable for women and children.
I like it. Yeah,
Also a yard.
exactly. It's $24 billion. So you solve that question, it's a $24 billion value. And I think with that, I'm going to quit. I can go on a lot of different things, but the point here is that what you want to do is looking at the fundamental properties of the materials you're working with. If you're talking about structure, like structural engineering, and then we can get into all kinds of other discussions on thermal and this or that. But the pounds per square inch is an extremely important concept. If you know those 3 or 4 different orders, the 100,000, the few thousand, the sub-thousand, steel for 100,000, rock and plastic around 5,000, wood under 1,000, like 300 for standard SPF, spruce fir pine, spruce pine fir, that's what they call SPF lumber.
So
That's the
for,
stuff at Menards. They rate it at 300 psi.
For a steel trailer,
Yeah.
is that the limiting factor for the load weight limit? Is the tires? Are the tires?
Well, you can get tires that are rated for, you can get an axle that's up to 15,000 pounds. So not necessarily, but it's going to be the flex, like the flexing, like for example on my long dog, when you load it down, I mean it starts to sag in the middle. So let me finish this discussion off with the ultimate in structural design, and you've heard of this, it's space frames. Because of this issue that I discussed about the flexion, like a long piece will just sag down, or a long piece of lumber will just wobble like that. For that reason, you set up geometry, you get into biomimicry here. How are like plankton shells made, or like, what's a good example of a skeleton thing? I mean, whether it's domes, it's structures in space, they always have space frames. That's why they're called space frames. Because they take the least material for the amounts of forces they can withhold. So space frames, what I mean by that. And this is what we're going to do later here.
The sacred geometry already shows us what are the most stable structures.
Frames. Frames. So we did all kinds of. This is called a space frame.
Yeah.
This is made of rebar, and it's in 4 dimensions, and it's got cross members. So you're addressing all those forces by triangulations and so forth. This is actually what we were thinking of doing the rapid learning facility, but we might actually put that on the 2nd floor, whatever. Or use this as an exoskeleton for the existing structure to build a 2nd floor on. So our structure, we're designing so you can expand it. Space frames that look like that. You can do various standard frames. Like this is somewhat of a space frame too. It's minus the triangulations, but basically where you're embodying 3-dimensional space instead of having like a flat thing or a tube or even an I-beam. Because an I-beam, for the same amount of steel that you will put into an I-beam, you can do the above and get much more strength. So what's the space frame trailer look like? It could be, for example, those long trusses, 20 feet. Let's say you want to make a 20-foot trailer. Lay a bunch of them that are 1 foot tall all next to each other, and that is probably going to be better than any kind of super thick, half-inch web I-beam that you're going to do, because it resists forces in all directions. And if you're making buildings, then you can do space frames like that. You can do cubical structures where each side is those space frames. So in that case, you're using the least material for the largest amount of strength. And that's kind of how, when we do, for example, a trailer, we'd like to use more of this, because this is steel, and you can combine that. You can also, wood is quite good too, but wood happens to rot, so actually steel with concrete, if you protect steel from rusting, and concrete, they're quite sustainable by the lifetime argument, even though they take a lot of energy. Now, if you, of course, take those materials and turn them into solar concrete, solar steel, then you're absolutely doing a good thing.
What is that?
Well, technically, trees are solar energy.
They are solar energy.
So
when we do
Right,
solar
but
steel
solar
and solar concrete, we're doing biomimicry, the same thing that wood does. Wood does, that's a natural material that's grown from the sun. We can grow steel from rocks. That's a human-made process. So what's solar steel? Solar steel is when the induction furnace, which is an efficient heater for melting steel, is run by electricity from solar. And that's what we call solar steel. We're powering that process instead of doing grid electricity, which is produced from coal and at a burning power plant or whatever. Coal, nukes, and gas are still the main power supplies for civilization.
And that would be the same for the concrete.
Yeah, so you're just burning the rock with, instead of using natural gas, you're just using electricity to heat it and resist developments. So that's that. And it could be part of a closed loop material cycle. So I'm not opposed to steel and concrete.
How effective are solar smelters,
They're as effective as anything else. You're talking about, do you have electricity? If you have electricity, you're running an induction furnace. The induction furnace doesn't care it doesn't discriminate between grid and solar. It just
Except
says,
you can
I've got
run out of
electricity.
solar.
There's a problem there. So this gets into timing, and that is that the sun, you have effective power for 6 hours a day. 6 average.
Without clouds.
On a day without clouds, you might have 10 or 12, but 6 on average throughout the whole year, including all the sunny days, not sunny days. In this area, actually, it's the solar hours per day are about 6 in Missouri, right here. So you count that. Well, yeah. So you do that for 6 hours in the day. Now, if you integrate your biodigester for the facility, you're actually storing. You can store that gas and generate plenty of it from either biomass or we're mowing here. And we throw those mowing clippings into the biodigester. That's perfect food for biodigester. So you're talking about, you've got landscaping, but that actually feeds your electricity grid for the night, or for when you want to run your induction furnace 24/7, if you want to do that. But otherwise, you reduce, if you do have the PV, yes, the limit is, of course, that you've got 6 hours of sun. And that's why industry doesn't do it, because they can't just shut down their gigawatt, their multi-megawatt melter. They want to run it 24/7. They only take little breaks because it's inefficient to shut it off and turn it back on. The smaller you go, the more efficient it is, because it takes a much shorter time to heat it up and getting up to temperature. So it's actually, in a distributed way, you can do more with solar. But it's basically about an issue of design. Nobody ever designed the solar systems, because, as I said, when I started this project, solar was what, $4? It was 20 times. Right now it's 20 cents a watt. Before it was $4 a watt. So what's the difference? That's 20 times. 20 times 20 cents is $4. So only a few years ago, this was absolutely unaffordable to do that. What I just proposed: solar steel, solar concrete. That became possible about 2016, a few years ago, where the cost went just so low. It's just crazy.
It's low right now, but it could go up again maybe. But if you've got solar panels, how often are they needed changed? Like, how often do they break outside of, like...
Their lifetime for a standard solar panel is 20 to 30 years.
Okay.
So you're talking, you produce them once, there's nothing that goes bad in them.
So no
They have
hail,
no moving
nothing
parts.
really.
If you get hail, you might. I mean, they're typically hail-proof, but if you get a really bad hailstorm, maybe they crack. But I mean, they're rated for. They've got the super strong glass,
Okay.
tempered glass on it. So, yeah, I'm sure you can break them with hail. But
So what happens after 30 years? Like if they really don't?
yeah,
break?
but they're guaranteed, warranted for 20 to 30 years.
Right.
What's the warranty? They say 80%. So then you've got another 30 or 100 years when it goes down to like, over the next 20 years, it's going to go down to 60%, 40.
Okay.
It's insane. It just works. I mean, you got to look at the numbers there and understand those numbers because they're very favorable right now, and I couldn't believe it. And I got those panels for 20 cents a watt.
And the more panels you have,
That's why I got 120 kilowatts.
right? But I'm saying where you were talking about being able to store it, the more you can store, then, right?
You need to have storage.
Right,
And how do you
right.
store it?
You were talking the
Well-
the water?
For thermal energy storage for night, where we discuss that electricity can be replaced up to 70% because 70% comes to water heating, space cooling, and space heating. 70% of all electricity. So there we can get rid of 70% storage right there if you use the thermal storage.
Right.
And then beyond that, you can do things like split water to compress hydrogen, make hydrogen as a fuel source for the next hydrogen economy. That you can do. That's probably what the Earth is going to end up doing. Or you can do, there's the natural means like biogas or, just the biodigester stuff, which I think is, I mean, that's old technology that you can compress that gas to run engines or cars. I mean, they have natural gas cars, right?
So-
they're common.
If
And then you can
you're
have-
able to recycle it, then I know someone was asking if you were putting back to the grid because I know there are solar farms where they're actually having people buy their electricity from them
Yeah.
or whatever.
Yeah. Oh, you could do that, except the grid wants to pay you peanuts for it, so that's why we don't do it. They don't give you a lot for it. It's like a few cents. Whatever I looked at it, it's just a fraction of what you pay for it, what they sell it for. It's not. Our system is actually not grid connected. It's technically an off-grid system where it's got a transfer switch on it. So, yeah, we could connect to the grid and feed back to the grid. But then there's one trick to that where if the grid goes down, your house also goes down, even if you have PV in a day.
Unless
So
you
I didn't want to design that into.
switch.
Yeah, I was gonna say.
I didn't want to
unless you-
design an on-grid system. We wanted to go with a hybrid system, which is where if the sun goes out and it's day, you don't get shut down by the power company. You keep your power on.
And if the grid goes out, you still have electricity.
Correct. And if it's at night, well, at that point, yeah, your power goes out if you don't have the sun, if you don't
Can
have
you
any
have a
storage.
backup generator?
Of course.
I mean, so you still have.
Of course,
another
of course.
option.
Biogas.
Yeah, you got your biogas. So I think my comment these days on biogas is that could be the missing link for storage in terms of solar energy.
Biogas,
So-
as in,
Biodigesters. So you're
Oh.
fermenting.
like the people I told you, like the Simpsons, right?
Yeah. So I think let's leave it at that.
Yeah, Simpsons, right?
I mean, we could go on for all kinds of calculations. I'll keep refining this material, but the point is, know the basic first order of magnitudes, and then start applying that to materials, and that's it. Start getting used to it, and that way you can actually figure out more and get really good at understanding like why structures work and everything else. Yep. We'll leave it at that. Thank you for watching, and we'll tune in again tomorrow.
Oh, yeah.
Okay, take care.
Good night.
Good night. So